Good morning, students. Today we will discuss measurement of force, torque and pressure. So as you know, force, it is the reaction between two bodies. This reaction may be tensile or compressive, whatever it is. And this force may be found out by direct method, indirect method. Direct method involves direct comparison with unknown gravitational force on the standard mass, example by physical balance. So study later on. Indirect method involves measurement of effect of force on a body. For example, measurement of acceleration, measurement of resultant effect, that is resultant effect is nothing but deformation. So these direct and indirect methods are used. Okay. For direct measurement, you can see the unequal arm balance is there. Just to see that unequal arm balance. So as a direct method is F is equal to ma, that is W. Unequal arm balance. Yes, it is unequal arm balance. Just you see the sketch. So this is the lever, this is the tensile force acting downward, and knife edge P, and this is the pointer attached. Here the scale is provided, and this is scale calibrated in terms of force. And here, so say this load arm is A, power arm is P, then this is Fg, gravitational force acting downward, and this is mass M, and the G is center of gravity. So before actual explanation, so you know this type of unbalanced force is used in sugar factories. You can see it in the sugar factory. So maximum application is in the sugar factory, or whenever so the very high weight is measured with a light or compact instrument. So this is very compact. So this you can use to measure the weights in terms of tons, 20 tons, 60 tons, like that. So just you can see it. And so maximum, you see this maximum application is in sugar factories, and wherever high force, that weighing of lorries, there also this type of balance is used. So the only thing is, by compact instrument one can measure so the heavy load in terms of tons. Okay. So just you see how it appears. An unequal arm analytical balance suffers from major disadvantage is it requires a set of weights required here. Okay, set of weights which are at least as heavy as maximum weight to be measured. An unequal arm balance is used for the measurement of heavier weights with help of lighter weights. The unequal arm balance uses two arms, this one and here. So this side, unequal arm. Okay. One is load arm, another one is power arm. These are unequal because it is not exactly the center. It is, so this side is lesser and this side is more. Unequal arm balance. So here it is knife edge. Okay, this side it is less and this side it is more. So that is why it is unequal arm balance. The load arm is associated with a load, that is the weight force. So this one, weight force, is to be measured, while power arm is associated with the power, that is force is produced by counterweight. required to set the balance in equilibrium. Okay, see that mass m acts as a power of beam and exerts a force of Fg due to gravity where Fg is nothing but m into g. Okay, force acts as counterposing force against the load which may be a test force Ft. So that we'll consider this is test force Ft. Okay. So this Ft is equal to Fg into B by A. B by this divided by this A. Okay. Then, so this is constant. That is Ft is equal to Fg into B by A. This is provided that G is constant, gravitational force is constant. Okay, and this type of unequal arm balance are more in use and more applicable. So just you see next to the platform balance, and the platform balance, you can see platform balance. It is multi-lever system, that is improved version of that unequal arm balance. As its name itself indicates, the more levers are used. So very important thing is when the levers are more and more, so you'll get the more magnification, more weight can be measured easily. Okay, see just you see the sketch. Before that, an unequal arm balance is not suited for measurement of large weights. When measurement of large weights are involved, multiple lever system. So this multiple lever system is more in use because whenever larger and larger weights are required, so this multiple lever system is used. A large weight W is measured. So large weight W is measured. This is fan. W is the large weight. So just you see the platform balance. So this is platform. How many multi-lever? 1, 2, 3. So these are the levers. So this distance we can say this is poise weight, beam scale, adjustable pointer is there, and say this distance is A and this is B. Tensile, then levers. So it is multi-lever balance. So this distance, this is F from here to here. Here it is D, C, E, H. So the notation you can take anything. So it is left to you. But this is the W weight. Okay, W1, W2. Actual weight W is this one. Then, in terms of two smaller weights, WP and WS. WP and WS and WP. WP is poise weight. Okay. WP is weight of poise. WS is weight of fan. The system is provided with adjustable counterpose which is used to get an initial balance. Before unknown load, W is applied. Before unknown load, W is applied to the platform. The poise weight WP is set at 0 0 of the beam scale, and the counterbalance is adjusted to obtain initial counterbalance is balanced initial zero balance. Okay, in order to simplify the analysis, it is assumed that weight W can be replaced by two arbitrary weights W1 and W2 arbitrary weights, W1 and W2 arbitrary weights. Also, it is assumed that the Poisson weight WP is at 0, and when the unknown weight W is applied, it is entirely balanced by the weight Ws. So this Ws. Okay. Then, if it is correctly balanced, then one can measure the weight. So this is the only concept of this one, and we can go for next. Next one is proving ring. This device is long been the standard calibrating tensile testing machine, and is in general the means by which accurate measurement of large static loads may be obtained. A proving ring is a circular ring of angular cross-sectional area. Let me see, angular cross-sectional area. This is proving ring, and this is F force, and this one is micrometer wheel, vibrating reed, proving ring, and this is F. Okay, where F is the force, E is the Young's modulus, we can say. Just we can say E is the Young's modulus, and I is the moment of inertia of section about the central axis of bending section, and D is outside diameter of the ring. Y is the deflection. Then the equation derived under assumption that the thickness of ring is small. The thickness of ring is small compared to radius. The thickness is small, so that is neglected. And also it is clear that displacement is directly proportional to the force. Since the deflection obtained is very small, the usefulness of proving ring is calibrated device depends on the accuracy with which this small deflection is measured. This is done by using precision micrometer, and in order to obtain precise measurement, one edge of the micrometer is mounted on the vibrating reed, which is plucked to obtain a vibratory motion. The micrometer contact is moved. Forward until a noticeable damping of the vibration is observed. Okay, so proving ring is normally used for a measurement of force within the range of 1.5 kilonewton to 1.5 meganewton. The maximum deflection is typically of order 1% of outside diameter of the ring. This much only. Okay, then come to the next bit, torque measurement. The force, in addition to the effect along this line of action, may exert turning effort related to any axis than those intersecting the line of action. Such turning effort is called torque. So just torque is equal to, see it is torque, we can say it is couple also. Couple is equal to FB1 FB1 minus FB3. FB1, FB1. The couple action. So see, this couple action means it is equal in magnitude, opposite in direction. Okay, this is one F, another F. So we can say couple or torque is F, this FB1 minus FB3, and this is O is considered. So this is nothing but FB2. This is nothing but FB2. The important reason for measuring torque is to obtain load information necessary for stress or deflection analysis. The torque T may be computed by measuring of force at unknown radius r from the relation. So that we see the relation. See this relation. T is equal to Fr. Okay. However, torque measurement is often associated with the determination of mechanical power, that is, the power required to obtain a machine or power developed by the machine. The power is calculated from the relation P is equal to 2 pi Nt. Okay, just to see this one. It may be that this absorption dynamometers, driving dynamometers, transmission dynamometers. See where n is angular speed in revolution per second. Torque measuring device are used. In this connection are commonly known as dynamometers. These dynamometers, as I told, absorption dynamometer, driving dynamometers, transmission dynamometers. Okay. Next, we see dynamometer, mechanical dynamometer, that is Prony brake. That is Prony brake. You see, this is mechanical dynamometer, Prony brake. Just you see, this is the tightening arrangement. This is a rope. This is flywheel from the machine, and these two are wooden blocks. This one and this one wooden blocks, and this is the lever, and this is the force. They say this length from center of the wheel to F is L. Okay, two wooden blocks are mounted diametrically opposite on the flywheel attached to the rotating shaft, whose power has to be measured. One block carries a lever, so this block carries a lever and lever arm, and an arrangement is provided to tighten the rope which is connected to the arm. So this tighten. Okay, connected to the arm. The rope is tightened so as to increase the frictional resistance between the blocks. In order to increase the frictional resistance between the blocks and the flywheel, between the blocks and the flywheel. The torque exerted by Prony brake is T is equal to F into L. Okay, where F is force measured by conventional force measuring instruments like balance or load cells, etc. The power dissipated in brake is then calculated by the equation. Just to see, by this equation we can see K is equal to 2 pi Nt by 60, or this is 2 pi FLN by 60 watts. So where F is in newtons, L is length of lever in meters, N is angular speed in revolution per minute, and P is in watts. Okay, and this much is about Prony brake. Neat sketch is required, arrow mark is shown. So neat sketch and brief explanation about the sketch is more than sufficient. Okay, go next. This is Prony brake is mechanical dynamometer. One more dynamometer, hydraulic dynamometer. Just see hydraulic dynamometer. Yes. This is housing. This is shaft. And this one is a reaction arm, force measuring system. This is shaft. And this is a radial blades. This is inlet water. This start with this inlet water. That is water. It is outlet. Okay. The typical hydraulic dynamometer is shown in the sketch. Just to see. The capacity of hydraulic dynamometer is function of two factors, speed and water level. The power consumed is a function of Q of the speed approximately. The torque is measured with the help of reaction arm. Okay. The power absorption at a given speed may be controlled by adjusting water level in the housing. Water level in the housing. This type of dynamometer may be made in considerably larger capacities than the simple Prony brake, because the heat generation can be easily removed by circulating water into and out of housing. Water into and out of the system. So heat generation will be reduced. This dynamometer, the power absorption element is the housing, which tends to rotate with the input shaft of the driving machine. But such rotation obtained by force measuring device, such as some of the scales or loads placed at the end of the reaction arm. By measuring the force F, the known radius R, the torque T may be computed by a simple equation. You can see just T is equal to F into R. Okay, so this is not required. We go next. Just it is not required for this one. The current dynamometers is not required. So just DC dynamometers not required. Just to see. Next. Pressure measurement. Pressure measurement just to see. Pressure measurement is represented as a force per unit area, as you know already, by a fluid on a container. The standard SI unit for pressure is Newton per square meter or Pascal. High pressures can be conveniently expressed in kilonewton per meter square, while low pressures are expressed in terms of mm of water or mm of mercury. That we know already. And this is simple pressure, zero absolute pressure, barometric pressure is up to atmospheric pressure, and more than that this is total or absolute pressure, and here it is absolute pressure, negative pressure, positive gauge pressure. This plus this itself is the absolute pressure. Sorry, this plus this itself is the absolute pressure or total pressure, we can say. This relation you know already. Okay, just it is not required. Static and dynamic pressures. A fluid is in equilibrium. The pressure at a point is identical in all the directions and independent of orientation is referred as static pressure. Okay. In dynamic pressures, there exists a pressure gradient within the system. To restore equilibrium, the fluid flows from the regions of higher pressure to regions of lower pressure. Okay. Next, the very important pressure measuring instrument is the Michelide gauge. Just go there. Of course, the Bridgman and Bourdon tube gauge, diaphragms, bellows will study later on. So this Bourdon tube pressure gauge you know already. So this is also used. But the new concept is Michelide gauge. So just we go to Michelide gauge. Yes, Michelide gauge. And you see the sketch of Michelide gauge. Okay. See, this is 2 vacuum space P. It is shown like this, and capillary tube. See, bulb B, opening here, the opening O it is, and mercury is filled. This reservoir is movable reservoir. Okay, a simple sketch is there. So just scales are provided here. Okay, just by this we can say the Michelide gauge is modified mercury manometer. Modified mercury manometer is as shown. The movable reservoir is lowered until the mercury. The movable reservoir is lowered until the mercury column drops below O. Okay. Bulb B. So bulb B and capillary tube C are then at the same pressure as that of the vacuum pressure P. The reservoir is subsequently raised until the mercury fills the bulb and rages in the capillary tube. So here, at a point where the level in the reference capillary R is located. This R is located. Just you see, R is located. That is reference capillary. If the volume of the capillary tube per unit length is say A, then the volume of gas in the capillary tube, say it is AY. It is AY. AY means what it is? Just you see. AY. A is the length of capillary tube occupied by the gas. A we have taken that capillary tube per unit length. A we have taken A. Y is the length of capillary tube. Okay. Then one can just see. PC is equal to PV by VC, because PVB is PCVC. Okay. Then PC minus P from this equation. PC minus P is Y. Okay. We know that PVB is equal to PCVC. So substituting these values of PC from equation 1 and 3 respectively in the equation 4, we will get this one. Okay. And just to simplify, we will get P is equal to AY square divided by PB minus AY. Usually AY is lesser than this one, VB. Vacuum pressure P is AY square divided by VB. Okay. This is about in commercial McLeod gauge, the capillary tube is directly calibrated in micrometers. The gauge is sensitive to condenser vapors, which may be represented in simple form because they can condense upon compression. For dry gases, the gauge can be used from 10 to minus 2 to 10 to 2 micrometer of pressure. Okay. This is about McLeod gauge. Then, so next one is Pirani gauge, Pirani thermal gauge. So just you see Pirani thermal gauge. Before that, the temperature of a given wire through which an electrical current is flowing depends on, first one, the magnitude of current, second, resistivity, third, a rate at which the heat is dissipated. The rate of heat dissipated largely depends on the conductivity of the surrounding media. As the pressure reduces, the thermal conductivity also reduces, and consequently the filament temperature becomes higher for a given electrical energy input. Okay, this is basis for two different forms of gauges to measure low pressures. Okay. Just a minute. For this, you can see it here. Pirani gauge. The Pirani gauge that you see here. The bridge circuit. Heated platinum filament it is. Heated platinum filament. Vacuum pressure. Okay, just it is the diagram. It operates on the principle that if a heated wire is placed in a gas chamber, then the thermal conductivity of gas depends on the gas pressure. Therefore, a transfer of energy from wire to gas is proportional to the gas pressure. If the supply of heat energy to the filament is kept constant, then pressure of the gas is varied, then temperature of the filament will alter, and is therefore a method of pressure measurement. Okay, so this is a single one. In the similar way, double also you can use vacuum pressure. Okay, it also works on the same principle, but okay. Next we'll see. So this much is more sufficient for Pirani gauge is more sufficient. So one more thermal vacuum gauge also will come. So it works on same principle as that of Pirani gauge, but differ in the means of measuring the filament temperature. In this gauge, the different temperatures is measured directly by means of thermocouples welded directly to the gauge. Just to see that also. Last, see, this is thermocouple, moving meter, metal or glass envelope, heater filament, this is heater filament, vacuum pressure. Okay, this is more than sufficient, and you go through that. Line diagram is important and concept is also important for it. Okay, thank you.